Good morning and welcome back. Today I thought we would do a video where we speak about open loop control, closed loop control, which is also known as feedback control, and then feed forward control. Please sit back and relax as we go through the different aspects. Let's start off with open loop control, which is always going to be a very interesting option that we can encounter. Now, open loop control is when you do something without checking if it has worked. Imagine you've possibly got a sprinkler system in your garden, and I've got one, and mine switches on every single evening at 6 o'clock, so at 1800 hours and 0 minutes and 0 seconds. That's when it switches on. That sprinkler system does not care whether the lawn or the garden is already wet or whether it is dry, whether it is summer, whether it is winter. It does not make a difference. It just gets told to run for 10 minutes, and that is what it's going to go and do. It's very much the same as if you were possibly to use a toaster and make a piece of toast in the mornings. You've got your toaster which sits in front of you, and you take your piece of bread and you put it inside, you push the button down, and it does the toast. There's no sensor that's going to look at the color of the toast. It's going to purely work on a timer. You take something like your oven and you switch it on for 20 minutes, and you then go and use the oven without checking the temperature at all. So we can say that it's when you are going to set something and not look back. You tell the system to do something, but the system does not tell you if it is right at all. Now, how can we look at this from a technician point of view? Open loop control is when we're going to send a command signal without using any feedback from the process variable itself. I don't have a controller that's going to measure the output. It's simply going to follow the instructions that have been given to the process itself. So there's no measurement. There's no process variable as such, which we're going to have a look at. There's not going to be any correction of an output which needs to be taken up or down. It's only going to work when a process is predictable, but it is a nice, cheap, simple, and fast method that we can go and use. Yes, it may drift if things go wrong and if there is a disturbance. For example, you might have a chemical dosing pump that injects 5 liters per hour, regardless of the actual tank concentration. So if the level does change, or if the chemical strength varies, the pump will still inject 5 liters per hour because it's not going to have any feedback whatsoever. So in summary, we can say that a technical description would be that open loop control is going to have a fixed action with no checking and no correction whatsoever. If I was to go and write a book, then I would say that we do something and then we walk away immediately. Great. Now let's step it up a level and speak about feedback or closed loop control. This is when you're going to check what's happening in a process, and if there's something wrong, you need to fix it up immediately. You know, you and I do it every single day of our lives. You might have a glass of water and you go and fill up that glass of water. What are you doing? You're watching the level, and if it gets too full, you slow down or you stop the water addition. If it's still low, you can keep pouring more water into it. So all the time you're looking, you're thinking, and you're adjusting. You know, if I've got a process over there and I've got an instrument and I'm measuring the signal from the instrument, which we know is the process variable, this is where it's going to get to a point where we're going to have a look at the signal, compare it to what we would like it to be, and from there we can go and take the action. You and I do it every day in our lives. If you're steering a bicycle and you watch where you're going, that's going to be feedback control. If you're playing with the volume control of your TV and you take the volume up or down, depending on how it sounds to you, that's going to be feedback control. Maybe you're going to be baking some cookies and you want to check whether they are going to be brown enough. So you measure what's happening and you change what you're doing to keep things right. As engineers and as technicians, we would say that feedback control is when a controller continuously measures the process variable and adjusts the final control element to keep the variable at set point or at target value. From a technical point of view, the controller reads the process variable, which could be level or temperature or pressure or flow, pH, conductivity, you name it, doesn't make a difference. It compares that to the set point, and remember, it gets an error. The error is going to be the difference between the set point and the process variable. So that's going to be my feedback loop. If there is an error, then the controller will change its output, and the loop is going to keep correcting until there is no error, until the process variable and the set point are going to be at the same value. You can think of many different examples. What about a temperature controller on a heater? In that case, my process variable is going to be the actual temperature. The set point is going to be the desired temperature where we would like to go and operate. If the process variable drops, the controller will open up a steam valve or switch on the heating element and the temperature will go up. If the temperature is too high, then the steam valve is going to be closed or the heating element is going to be switched off. And the loop is going to do this over and over and over again. So we as engineering people like feedback control because it handles unmeasured disturbances. It corrects for drift, noise, as well as process changes. It really is the backbone of almost all industrial control loops. We've already dealt with the tuning of PID controllers. They are there to give us stability and responsiveness, and they're going to get used with a feedback loop. So a feedback is going to measure and compare, correct, and then repeat. Again, if I was to go and write my book on instrumentation, which I always want to, but which I never get round to, I'm going to say that in the case of feedback control, it's when I measure something to control that same something. That to me is going to be a feedback loop. And so we get to the last of the three strategies that I want to go and discuss today, and that is going to be feed-forward control. Now, feed-forward control is like fixing a problem before it even happens. Imagine you're riding a bicycle and you're going downhill with that bicycle of yours. You know that the hill is going to make you go too fast, so before you start going down, you press the brake a little. You're not waiting to get too fast. You're going to stop it before it actually happens. And that's going to be feed-forward control. You see something coming, which is the hill. You act early, which is to press your brakes, and you avoid the problem, which would be to go too fast down the hill. Now, as engineers and as technicians, we like to think about it a little bit more technically. So I guess we could say that feed-forward control uses a measured disturbance to adjust the process before the disturbance affects the controlled variable itself. There's my process that I'm going to go and have, and my process may be subject to various disturbances. Now, if I can go and measure those disturbances and take the correct action in advance, then we know that it's going to work perfectly for us. So in a normal feedback loop, the controller waits until the process variable changes and then it reacts. With a feed-forward control, it does not wait. It looks at something upstream that will cause a change and it takes the necessary action based on that. You might have a flow change that enters into a heat, and we know that that's going to change the outlet temperature. By means of feed-forward control, the incoming flow is measured. The controller calculates how much extra steam or fuel is required. It then adjusts the value immediately before the outlet temperature drifts. And please do go back to my video where I showed you combined feed-forward and feedback control. So in a nutshell, we can say that feed-forward control is actually going to be proactive. We already know that feedback control would be reactive. Feed-forward control does need a good model of how the disturbance is going to affect the process. And please do have a look when I do the advanced process control. I'm going to show you what a model is made up of. Feed-forward control really works best when a disturbance can be measured reliably. It's going to be often used in a combination with feedback control so that we can get some sort of fine control. When I get round to writing the book that I've always threatened to go and do, I'm going to say that when I measure one thing to control something else, that is when we're going to have a feed-forward control. Maybe I can do one more explanation over here. Imagine if I was to have something such as a tank, and I want to control the level inside that tank. And let's go and say that I've got a variable speed drive, and I want to control the level inside that tank. Now, what if I was to have a pipe bringing product in, and I go and put in a flow transmitter, which is now going to go to my feed-forward controller, and that is going to operate my variable speed drive. Can you see what's happening over here? I am measuring the flow in order to control the level. So I'm measuring one thing to control something else. If the flow increases, I will run the variable speed drive faster to pull the level down. If the flow decreases, I will run the variable speed drive slower so that we're not going to deviate too much from the level. In this case, again, we're being proactive. We're measuring one thing, and we're going to go and control something else. And that is it. I hope we've managed to put everything into perspective. See you with the next video.